50 artificial intelligence agents just scanned 466 million lines of government code in 20 hours. If a human team took on that exact workload, the estimated timeline wouldn't be days or months. It would be closer to 6.5 years. That specific timeline comes from an internal estimate by the Government of Alberta's technology team, recently detailed in a case study by Anthropic. While that 6.5-year mark isn't an independently audited benchmark, the sheer scale of the operation is undeniable. The scope of this scan covered the digital infrastructure for 27 separate provincial ministries. That totals roughly 1,280 different applications, spread across 3,400 code repositories. Those applications route and store highly sensitive information, including provincial tax records, government procurement data, and private social services case files. Decades of accumulated technical debt, outdated software, incomplete documentation, and unpatched bugs had created a vulnerability surface too vast for manual review. Securing that much legacy code required a completely different approach to maintaining public infrastructure. With nearly 500 million lines of code, pasting it into an AI breaks the context window. Instead, they built a two-stage filtration pipeline. First, a deterministic rules engine isolates known vulnerabilities. Second, parallel Claude code agents analyze the pre-filtered anomalies for deeper structural logic. The pipeline demanded strict proof. If the AI identified a vulnerability, it had to cite the exact file and line number, so human developers could instantly verify the finding. This hybrid architecture makes the process viable. Pairing a rigid deterministic rules engine with flexible AI agents filters out the noise, keeps the models grounded in reality, and processes massive amounts of data at extreme speeds. Finding bugs is one step. Fixing them is another. Claude code shifted from discovery to remediation. When it identified a vulnerability, it could often generate the fix, test it, and build the updated code directly. But the engineering team established a strict prerequisite. If an older application lacked the automated tests needed to prove a patch was safe, the AI was forced to write those tests first, before altering a single line of production code. In cases where the old legacy code was too complex to patch cleanly, the AI rebuilt it entirely. A government subsidy portal originally hand-coded in Java 25 years ago, which took 5 months to build, was completely modernized and rewritten in just 4 to 5 days. Alberta's team didn't stop at a single massive scan. They used the Claude Agent SDK to transition from a one-off repair job into a continuous security loop that runs alongside their developers. First, a red team agent simulates an external threat to map how a vulnerability might be exploited. Immediately, a blue team agent assesses the defenses and drafts a remediation plan. Every application is checked against 95 security controls on every pass. Using the Agent SDK turns cybersecurity into a parallel process. Instead of waiting for a manual audit every 6 months, the defense mechanism runs constantly, testing and securing code as it is being written. But let's pause here, because deploying autonomous AI inside government systems carries catastrophic risks. If a language model hallucinates a fix that breaks a critical database, or if an agent exposes sensitive citizen records during a scan, the fallout affects real people. To manage that risk, Alberta engineered deliberate friction into the pipeline. They established heavy, mandatory approval gates that intentionally throttle the AI speed right before deployment. There is an uncompromising division of labor. The AI is only authorized to propose patches and write code. Before any of that code ships to production, human engineers must review and approve every single line. Total automation in an enterprise environment is a massive liability. The AI's velocity is safe and valuable precisely because human developers remain the absolute bottleneck for final deployment. Extracting the core mechanics from this case study provides a blueprint for enterprise modernization. Step 1. Inventory the entire system. Step 2. Run a deterministic rules engine. Step 3. Demand exact line-level evidence. Step 4. Generate automated tests. Step 5. Heavily isolate permissions. Step 6. Maintain strict human responsibility for deployment. By running 50 agents in parallel, the team moved through the code estate simultaneously, rather than waiting for one human to finish one file at a time. While rebuilding a complex application still takes days, this approach finished the initial discovery scan for the entire province in less than 24 hours. These agents absorb the high-volume labor of scanning and drafting, clearing the backlog of technical debt fast enough for human engineers to focus on architectural decisions and final approvals.